Okay, in this video segment, what we're going to do is take this idea of our series circuits and our parallel circuits and then talk about what happens when you have a circuit that's complex enough that there's both series parts to it and parallel parts to it. Okay, and that's very common. Actually, it's probably the most common thing we get in our circuitry is some sort of combination of both put together. Okay, when that happens, we call that a network circuit. Okay, and our goal here today is to kind of give you an introduction to network circuits and what they are and kind of how they work. And then we'll have a follow-up video which dives deeper into the mathematical side of how do we solve for resistance and voltage and amperage within these network circuits, okay? So the first thing you have to think about is when you're looking at a network circuit, it's actually a combination of series and parallel. So the best thing to do mentally is to think, I have a circuit inside of another circuit, okay? And to do that, it's going to allow us then to break the circuit down into different parts, or maybe kind of like using orders of operation like you've done in your math classes before. Okay, so there really are two different types of network circuits, generally speaking, and we need to be able to determine which one is which as we look at those things. Okay, so you can have a network circuit like this one where you have something that everything runs, all the current runs through, and then it branches off into a parallel. Or it can branch first into parallel where you have things that have multiple things in series around them, okay? And what we want to do to start off is how to identify these different circuits for us, okay? So let's kind of go through that process together, okay? To do that, we have basically three questions to ask, okay? So if you can follow this three-step process, you will always be able to pick out what kind of circuit you have. And you might be asking, well, why do I care? Like, why do I care what type of network circuit it is? Well, you care for a couple reasons. One, you're an amazing person and you care about lots of things. And two, in terms of the physics stuff, the math you're going to choose to do is going to be dependent on which version of the network circuit you have. Okay, so mentally you had to make this decision before you can properly do your math. Okay, so here's our first question. First of all, is there only one path the current must follow? If this is true, and you say yes to this, you don't even have a network circuit. It's series only, okay? So this can jump you right to the part like, oh, this is just a simple series circuit. I'm going to use that. Then you ask, is there only one object, a resistor, a bulb, etc., not switch, not battery, but one object that in a separate path, okay? So only one object in those separate paths. If the answer is yes, then you have a parallel circuit, okay? And these are the two that we've already covered, okay? If this is no, okay, so you have more than one object within the separate paths, okay? So you said no here because there's separate paths. You said no here because you're like, wait a minute, there's separate paths, but one of the paths has more than one thing in it, okay? If that answer is no, you now have a network circuit, okay? So this is stuff that we've already kind of covered. Now the last part here, is there one object other than a battery or a switch that all current must pass through, okay? So looking at the circuit, is there one part of that path that all of the current has to pass through before you find the branch, or even after the branch? It doesn't matter if it's before or after. If it is yes, you now have a series circuit with parallel parts inside of it. If the answer is no to that, you have a network circuit that's parallel with series parts inside of it, okay? So identifying that is going to be helpful to us, okay? So let's take a look at some examples of that. So here's four different examples. We have example 1, 2, 3, and 4. And look at example 1. Here's our battery. We start the battery. We're going to work our way around, come around. Okay, here's a resistor, here's a resistor, here's a resistor. I see 1, 2, 3 resistors. I can only go one pathway, so that is just a series circuit. We've done those before. Okay, going down to number 2 now, come from my battery, and I come around and I see, okay, here's a resistor, good. All the current has to flow through this resistor, and now I have it split. So now some of the current can go here, and some of the current can go here. So this is not series, it's not parallel, because we have this one here, okay? So then we have to go back to that third question in terms of, do we have a place where multiple pathways are in here? So because all the current can flow through this resistor and then it splits, we know that the overall system here is series and we have a parallel component inside of that. Okay, so these two, R2 and R3, are actually in series with R1, but R2 and R3 are parallel with each other. Okay, So in this case, we have a series circuit that's a networked with parallel parts to it. Over here, we have parallel, parallel, parallel. We have nothing that has all of the current has to flow through it, right? Because current can make a choice to go through R1, R2, or R3. They don't have to go through any one of those. So because they always have optional pathways, these are all just parallel to them. In 4, we have our circuit coming from our battery, and we have a split. So we know we have parallel, but within one of the pathways, we have more than one resistor. So we actually have a series inside of our parallel network, okay? So in this case, we have a parallel network with series parts inside of it, okay? So that's what we're kind of looking at for our different determinations. Now, let's take a look at that through the lens of our FET application. So if we look here, I built 2 different circuits, and here's our first one. If we double check it, we come up, the electrons flow into here, it splits, so we know we have parallel, but I have a resistor and a bulb. So here's a series that's inside of this parallel network, okay? So we have a parallel network with series parts. Over here, I have first a resistor that all the current has to flow through. Notice how they can't get around it. And then it splits. So here I have a series network with parallel parts inside of it. Or you sometimes say parallel inside a series, okay? And the reason why I show you this is because it results 2 different things, right? By putting the resistor inside of here, I can have this 10 ohm bulb be dimmer than this 10 ohm bulb, okay? So you can actually change how that circuit works. Over here, by putting the resistance outside, this one resistor now can control how bright either of those bulbs are, but they will always be the same, okay? So depending on the goal of the circuit, you might want to have different brightness if you're using 2 bulbs, or you might want to force them to be the same if you're using 2 different bulbs, okay? So again, it's how you want to build your network circuit is what we're taking a look at here and how those things work, okay? Now mathematically, that's going to cause some issues because we have different math for resistance and voltage and current flow in series versus parallel. And that's kind of the next piece of this puzzle, okay? So I have a couple more examples to show you. So we're going to jump to a little bit different video clips of me showing you those. Thank you. Here we have a simple circuit, and what we're trying to accomplish here is, if you can think about this, is we have an LED right here, and we're making a flashlight, okay? So if we want to make a flashlight, a lot of flashlights have a power button, and then they actually have to have a bulb that turns it on. So our goal with this circuit is that when we turn the switch on right here, we're going to have the power button turn on that allows us to show that, yeah, there's battery power, the flashlight is working. And then we have the button over here that once we hit the button, will light up the actual flashlight, okay? So if the person wired this properly, we're going to need to have a parallel circuit to allow them to happen. Now, because of this diode, it has a need to have at least 100 ohms of resistance along with this circuit. Otherwise, this diode actually is overpowered and it actually can burn up that diode. So we need to put another resistor in this circuit somehow, which then creates a network circuit. So right now, if we take a look, we have a pathway that runs to here, it splits, which means I have a parallel part of my circuit. But then it comes back together and all the current flow has to pass through this resistor, which means I have a parallel component inside a series circuit, because these 2 together are in series with this inside of my my circuit, okay? That's how I have it currently wired. So if I turn on my switch, sure enough, we get our power source. Okay, good, the battery's powered up. I'm ready to turn my flashlight on. I hit my button. Well, that's not good. You know, we get the LED goes off, or the diode goes off, and the LED doesn't turn on. So whoever did this didn't wire it properly, okay? So they used the network circuit, but not the right way, okay? For this to work properly, what we want to have happen is we want this resistance to only be part of the diode, okay? So we still have a network circuit here, but now let's take a look at it. We have our pathway coming in here, it splits. Some of the current can go through the LED, some of it can go through the diode and the resistor and then back in. So this network circuit now is a series, because we have the diode and the resistor, they're in series with each other inside a parallel, okay? So we overall, this is a parallel circuit with series components inside of it, okay? This is a different type of network circuit. We try this one, we power it up. Sure enough, we get our LED, or sorry, our diode going, and it says, yep, you have power. And then when I want the flashlight to work, I can get the flashlight to work also inside of here, okay? So that's why it's important when you're building network circuits that you build them properly so you can get all the components to work the way you want to. And it's also why there's different types of network circuits, because sometimes you want things to always be in series, sometimes in parallel, and that combination is what people who build circuit boards have to figure out. Okay, we're recording this video actually inside my son's room. For Christmas, he got some LED lights that we mounted on his wall, and they look kind of cool, and he likes to play with them. They can change the colors from like blue to green to red. He can make it look kind of yellow in the room, or cyan or magenta, or just some combination of it. And we'll actually probably use these later in the year. We start talking about color. But for today, we're talking about circuits. And the reason why we come in here today is because this is a network circuit, the way this thing works. I can have all three colors on, or I can have just the blue on, or just the green, or just the red. And that's possible because the blue, the green, and the red are on different parallel circuits. It was actually one circuit, but they're on different pathways that are parallel to each other, okay? Which allows me to have one running and not the others. However, I can't turn off half of the red and half of the blue. I have to have all the red on at once or not on, which means each individual LED is in series with itself in the circuit. So the red is in a series, the blue is in a series, the green is in a series. And if I want to get some weird different colors, I can have, I can have my red and green on at the same time, or my blue and green on at the same time, or my blue and red on at the same time, which is fine, but I can also turn them off. Or I can have all three of them on if I want to and make it look almost white, okay? So what we have here is a network circuit where we have primarily a parallel circuit, but inside of each parallel pathway there is bulbs in series. So we would call this a parallel network with parts in series. Or sometimes we say it as you have series inside of parallel, okay? So two different ways of saying it. But this is just one example of how a network circuit, something very simple like some cool lighting in a kid's room, works. Here's another example that you may have experienced with. In chemistry, we often test for conduction inside of solutions. And we use a very simple little conduction meter. Depending on what chemistry class you had last year, you may or may not have used this. And this is a pretty simple network circuit that we see here. So what I've done is show you the picture of that, and then we kind of show you down here what it kind of looks like. So in this circuit, we have two different LEDs running. We have a switch, and then we have two probes that go down into a solution. So to simulate the solution, I just have another resistor down here. And we have our two different bulbs. Each bulb is actually a different type of LED, so they have a different amount of resistance through them. And the point of a conductivity tester is if you turn that switch on and you're testing for conduction. So the more resistance you get in the solution, which I can emulate here by changing my resistance down here, changes how bright the two bulbs are. Now we have a network circuit here because we want all the current flow from that battery to go through this resistor or go through that solution. So we want that to be in series with my two LEDs. However, the two LEDs, we want them to be parallel with each other because they have different resistance and they're going to give us two different visual results. So let's say as the resistance goes down and the solution conducts better, what we see happening is that the lower resistant bulb is going to start to light up sooner, okay? So that's going to indicate that we have some decent conduction inside my solution. So it's a visual cue using this very simple tool to check for conduction. But the more resistant bulb doesn't light up as bright. Okay, so it's showing weak conduction. Now, as the resistance goes down and that solution becomes a better conductor, what happens is the other bulb starts to brighten up too. So what can happen is we actually can see that we can use this network circuit to test conduction of a resistor or something else by building a simple circuit. So here we have both the bright bulb, the low resistance bulb is very bright now, and the other high resistance bulb is even lit up also. So this would tell me, using this tool, this conductivity tester, that there's very little or no resistance flowing through that solution. So that would be the case if I had like really concentrated salt water here. I could get almost the equivalent of a copper wire in terms of my conduction, and that would tell me the current flow. So again, whoever builds this has to kind of know that, because they want to have the proper type of network circuit. In this case, we have a series circuit that's networked with parallel components inside of it, or otherwise sometimes you say parallel inside a series. Okay, so just another example where we see a very simple circuit, but it's still a network circuit that we use.